A positively charged mass of 1 times 10 to the minus 4 kilograms is suspended from an insulated thread 0.20 meters long. When another sphere of equal charge is brought nearby, the suspended sphere is displaced by a horizontal distance of 0.1 meters from its equilibrium position. What is the electrical force of repulsion between the two equal charges? So this question might be a little misleading because we don't really need to apply any of our knowledge about electrostatics at all in order to solve it. Basically, the only thing that we need to know here is that like charges repel. So initially, we have our sphere hanging like this, completely vertical. It feels its weight force downwards and some tension force upwards. And these two forces are balanced, which is why the sphere is initially at rest. Then we bring a charge near to our sphere. Let's say we bring it on this side, and that causes the sphere to be repelled in the opposite direction from where we present the charge. So then we'll have a scenario that looks something like this. So maybe our dummy charges right here. So now in this scenario, our sphere still feels its weight force directly downwards, but now the tension force is directed at some angle up and to the left, since the tension force has to follow the line of the string by which the sphere is suspended. So looking at this, the forces can't be balanced since we have some horizontal component in our tension force. So for the sphere to remain in this position, we know that there must be some other horizontal force acting on the sphere, and that, of course, is our electrostatic force due to this small charge here that we introduced, which caused this whole shift in the first place. So now, looking at our free body diagram of our sphere here, we can write the net force in the y direction relative to some angle theta is going to be our tension force times cosine of our angle theta minus our weight force, which is mg, and this will be equal to 0, of course, since the object is at rest in the vertical direction. Now, our net force in the x direction will be similar. So this time we have the horizontal component of the tension force, which will be T sine of theta, opposing the electrostatic force, Fe, and this will also be equal to 0. Okay, so now what we need to do is solve for T in these equations. But before we do that, how about we go about finding the measure of this angle theta. So the key piece of information, or couple pieces of information, that we're going to need to employ to solve for this angle theta, one is that the string has a length of 0.20 meters, and the other is that the sphere is horizontally displaced by 0.1 meters. So initially the sphere was hanging vertically. Its horizontal displacement relative to its initial vertical starting position will be 0.10 meters. So this actually gives us a bit of a triangle that we can work with. So one side, if I take this triangle here, actually I'll redraw it in exactly the same orientation. I was going to say I'll flip it, but it's probably a little bit less confusing if I redraw it in its original orientation. So we have a triangle here. This side is the string. This side is that 0.1 meter displacement. 0.20 meters here, 0.10 meters here. We want this angle theta. So we can find that angle theta by using the inverse sine ratio. So remember, the sine ratio is the opposite over the hypotenuse. So opposite over hypotenuse. So the inverse sine will allow us to find the angle since we have both the opposite and the hypotenuse. So we take the inverse sine of opposite over hypotenuse, which is 0.10 meters over 0.20 meters. Meter units cancel. We basically have sine inverse of 1/2. So you can plug this into your calculator and you'll find that our angle theta should be 30 degrees. Okay, so now we can go back to our sum of forces relationships here to solve for the tension force in the y direction. Then we can substitute that value in to our net force in the x direction to solve for the electrostatic force. Now, that seems like a bit of a process, so let's take it step by step. So in our net force in the y direction equation, we have t cosine of theta minus mg equals 0. If we add mg to both sides, we'll have t cosine of theta, which we now know is 30 degrees, equals mg, which means that t will be equal to mg over cosine of 30. So mg will be 1.0 times 10 to the power of minus 4 kilograms times g, the gravitational acceleration, 9.81 meters per second squared. We'll divide by cosine 30 degrees there. If you plug that into your calculator, you should get t equals, let me just pull it up on my calculator here, 1.1328 newtons. And now if we substitute this into our net force in the x relationship here, so if we add the electrostatic force to both sides, we add plus Fe to both sides, we'll end up with Fe, the electrostatic force, equals t sine of theta. If you plug t in there and 30 degrees in for theta, we'll end up with 1.1328 newtons times sine of 30 degrees. Evaluating that using your calculator should give you 5.66 times 10 to the power of minus 4 newtons as your answer for the electrostatic force. Now if we actually round that to two significant figures, we can say that that is 5.7 times 10 to the power of minus 4 newtons. So that's the answer that we're looking for in this problem. Like I said, a little misleading since we don't really need to apply any of our knowledge about electrostatics. This is more of a Newton's second law problem. So hopefully this video helped you solve it.